In this video, I'm going to present our work on dimensionality reduction of convection-dominated PDEs using the proposed approach low-rank registration-based manifolds. In scientific machine learning, we are often interested in dynamical systems or physical phenomena that are governed by partial differential equations. And we often have access to these governing equations using first principles, and they can be written in the closed form of equation 1. When we have the rate of change of the state parameter as some known function of the state parameter and the special derivatives. We can actually solve these equations to the machine precision using the approaches that have been developed over the past few decades. But the problem is solving these equations becomes very expensive very fast. Sometimes we need to solve these equations for a couple of days on clusters of computers. So in this paradigm, the challenge of a machine learning model is going to be have the solution at the fraction of the cost of these traditional discretization models. And this is only possible if we can reconstruct the solution, if we can represent the solution on a low-dimensional manifolds using a few number of bases. And this becomes specifically a challenging task for an important category of problems, convection-dominated PDEs. So in the next few slides, I'm going to showcase the challenges of such problems. For the first example, let's look at the problem from computer vision tasks. So since 80s, we know that if there is some kind of a traveling features or rotating features in the snapshots, the low-rank recomposition of this snapshot on a linear subspace is not the efficient way. So since then, we have been using nonlinear manifolds for the low-rank reconstructions. But let me demonstrate what the problem is with linear low-rank reconstructions. So here we have the snapshots of a rotating character A, and I want to reconstruct that on a linear subspace using POD. So POD minimizes the Frobenius norm distance between M, our snapshots, and M tilde, the low-rank reconstruction of the snapshots. So rank of M tilde here is K, and K is much smaller than the dimensional of the problem. So we solve this minimization problem that actually has some closed forms, and let's reconstruct that on a subspace of size 1, as in figure 3. And you see the solution is nothing close to the snapshots we had. So how to address this challenge? The answer was using nonlinear manifolds. And for the next example, I'm looking at one of these. So here we have the Viscous-Berger's equations, and I'm going to use nonlinear neural networks to map the solution from the high-dimensional space to the low-dimensional space. I'm going to use the same architecture to map, to decode the solution from this bottleneck, this low-dimensional subspace, to the high-dimensional physical space. Then I have to be able to evolve the dynamical system on this bottleneck, on this low-dimensional space, so I'm going to use recurrent neural network for that. So in figure A, I have the solution of Viscous-Berger's equation of fluid flow for time between 0 and 1 with a Gaussian initial condition. So this initial condition convex in time and also forms a shock and diffuses. So I'm going to use these snapshots to train my architecture of neural networks for both mapping, the auto-encoder mapping, and the recurrent neural network, the dynamical system on the low-dimensional manifold. And the solution is plotted in figure B for k equal to 10. So the size of the bottleneck is here 10. For accurate comparison of these two snapshots and low-rank recomposition, I have the Frobenius norm distance normalized plotted as an error in figure 3. You see the error decreases as we increase the size of the bottleneck. But some might argue this is not the most efficient reconstruction on the nonlinear manifolds. I don't want to yet address that issue. But let's see what happens if I evolve my model beyond the training range. So here I have plotted the solution from t equal to 1 and 1.5 for both the exact solution and the output of the neural network in figure B. And you see here the solution doesn't depict the convection underlying the physics of the problem. So although we use a nonlinear neural network, This nonlinearity alone cannot represent the convection underlying the snapshots, and the error is not going to be decreasing even if we increase the size of the bottleneck. This challenge is known as large Kolmogorov end-width barrier that corresponds to a slow rate of decay of the singular values of the snapshots. So we know that a low-rank reconstruction of the snapshots of convection-dominated flows are not possible or efficient on low-dimensional spaces. So approaches like POD, proper orthogonal decompositions, or DMD, dynamic mode decompositions, that provide us with the linear subspaces are not the efficient way of constructing our reduced order models. However, these models are still commonly used in engineering community because they provide some interpretable and meaningful latent variable or mapping. For example, POD captures the most energy containing bases of the snapshots, or DMD approximates the nonlinear system with the linear systems. But to address this inefficient reconstruction, we know we have to use nonlinear manifolds like ISOMAP or TSNE or neural network-based autoencoders. And from these models, only neural network-based autoencoders have been used to successfully reconstruct the model on this low-dimensional subspace or manifolds. And one of the breakthroughs are deep convolutional neural networks and Galerkin projection that have been developed only this year by Lee and Karpberg. They also have a complementary work today that I suggest you follow if you are interested in the topic. So we are looking for a dimensionality reduction approach, which is nonlinear, so a manifold learning approach that provides us with a two-way map from the high dimensional space to the low dimensional space and vice versa. A property that not many of those previous slides manifold learning approaches provide. We also want to have some interpretability into the latent variable or into the mapping, so we can use the approaches, the tools that we had from the engineering community, and so the method is also useful for engineers and can work with the same tools that they already have developed. And for that, we are going to incorporate some of the physics of the problem. We don't want to oversaturate the problem with our assumptions from the physics. We want to just use enough of the assumptions that can provide us with an efficient reduction, but we for sure don't want to code the physics to the architecture, so we are able to actually learn from the data we already have. For that, I'm proposing low-rank registration-based manifolds. So in the next few slides, I'm going to illustrate our proposed approach. We have our snapshot matrix M of size n by k. This is high rank by our assumption, since this is the solution of our convection-dominated flows. We are looking for a map G from the high dimensional space to the low dimensional space, and we are also looking for its inverse from the low dimensional manifold to the high dimensional space. Think of this map as an abstraction in this slide. I'm going to make it more solid in the next few slides. So G inverse takes our latent variable from the low dimensional space to the high dimensional space. And M tilde is our solution, our latent variable, our mapped solution on this manifold. So since we want our manifold to be efficient, we want to be able to have M tilde to be low rank. So I substitute M tilde with UV, where U is a tall and thin matrix, and V is a short and fat matrix. And this can be solution of SPD and truncating the higher order singular values. In the next step, I'm assuming this map is just simply an interpolation between a time constant grid and a time varying grid. And I have another physical assumption in here. I'm assuming that this grid, which is moving in time or parameter space, is low rank. So I can have my grid points locations as UX, VX. where Ux is a tall and thin matrix of size n by r, and Vx is a short and fat matrix of size r by k, where r is much smaller than n and k. So this is going to be the heart of our problem. We are minimizing over the grid points Ux and Vx, and we are minimizing that distance. But there's a problem with this formulation. The problem is that our mapping is not providing a unique m tilde. It might even not exist. So there is no guarantee of a uniqueness and existence of m tilde given m, and vice versa. For that to happen, we need to impose diffeomorphism to the map. So G and G inverse both should be differentiable. And to enforce that, we should enforce bijectivity or one-to-oneness and smoothness. For bijectivity, we simply need to have our grid volume, our grid spacing to be positive in all the domain. And for smoothness, we can penalize any abrupt change in the grid spacing in both space and time. And then we are going to have the final form of the equation in 8, the low-rank registration-based manifolds. So once again, we are minimizing over Ux and Vx, which is going to be our time or parameter varying grid. We are also minimizing over U and V, which are temporal and spatial bases of this latent variable, the mapped solution, the mapped snapshots. We are minimizing that distance. And also we have the penalty terms here, gamma 1 Ux, Vx gamma 2 transpose, that are the hyperparameters that penalizes any abrupt change of the grid spacing. So they are proportional to the second derivative of the grid location or the first derivative of the grid spacing, however you want to think of it. And we want to have our grid spacing to be positive in all the domains, so we have that constraint. We are also often interested to keep the boundary points intact, so I have that as another minimization problem constraint. So now let's look back at our motivational problem. We had the snapshot matrix of this rotating character A, and we saw that the rank boundary construction of a solution on the POD subspace is not efficient, and there is a high error. So using the snapshots, I'm going to solve for the grid as in the proposed approach, the low-rank registration-based manifolds, as plotted in figure 3. You see the grid, the solution of this minimization problem, follows the rotation underlying the snapshots. And if I reconstruct my solution on this moving grid or parameter varying grid, the solution is much closer to the snapshots. To have a rigid body rotation, we have to increase the rank of the grid from 1 to 2. So I have done that and have solved the minimization problem for r equal to 2, so the rank of the grid equal to 2, and plotted in C. And you see the reconstruction of the solution on this rank 2 grid is closer to the snapshots. For the next example, I have the Euler equations of fluid flow, a nonlinear system of equations between the velocities of the flow, the density of the flow, and the pressure, and with the initial condition stated in figure. I have the solution. I solved that problem numerically and have my data, my snapshots as in figure 8. And as time goes on from figure A to figure C, you see as the time goes on, there's a shock, there's an interface that sweeps the domain, and that is the convection-dominated part of the solution of the problem. So I have the snapshots in the last time step plotted in figure A. Then I have my Eulerian grid, my time constant grid in figure B, and the low rank decomposition of the snapshots on this grid plotted in figure B. You see the non-physical oscillations here. And if I solve my minimization problem, I get the grid, the time varying grid, as in figure C. And now if I have my solution on top of this time varying grid, meaning that on my proposed manifold, I'm going to have a reconstruction much closer to the snapshots. So for better comparison of these, I have plotted the density, these snapshots on the diagonal of the domain in figure D, where the thick gray line is the snapshots. The dashed blue line is the traditional POD subspace, and the red line, the red solid line, is the reconstruction on the proposed manifolds. That is much closer to the snapshots. And comparing the error of the snapshots and reconstruction between two methods, for all the pressure, velocity, and density, you see we have gained some accuracy in our model for the same size of the low dimensional space. As for the next example, let's now go back to our Viscous-Berger's equation that I showed you that I trained once on a neural network architecture, and we saw that it was not efficient and it was not able to predict the convection. So what I have to do to take advantage of the proposed manifolds is just to train the same network on a proposed grid. So what I do is use the same data to solve my minimization problem and find out the grid, and then I have the grid, the map, so I can map the solution from the high dimensional space to this low dimensional space and train the same network on this map data. So I have G, the interpolation, I have G of M, that is the mapped solution, and I train my model on G of M as data. So I have the snapshot, I have the neural network autoencoder output, and then I have the output of this proposed approach in figures 3. And if I compare the error, you see the error on this low dimensional space is much closer to the snapshots, and the error is much lower to the traditional neural network approach. And if you remember, I couldn't get convection predicted using the previous approach, but now, since I know this convection, this identified grid is an approximation of the convection, I can extrapolate that in time and I get the solution and as in figure 3. And if I have the error, it is much lower than the error coming from the traditional neural network approach. And since this was a dimensionality reduction approach, I get all the benefits. So if I look at the training error in figure 14, you see that the training error of the neural network on this manifold, the black line, is much smaller than the traditional neural network, the dashed blue line. So in summary, we saw that the Kolmogorov n-width of the convection-dominated flows are large, so they are a challenge for efficient machine learning models. And the traditional and known dimensionality reduction methods are not either applicable or efficient or interpretable for our engineering tasks. So we propose the low-rank registration-based manifolds for the purpose of dimensionality reduction of such snapshots. And the solution on this low-dimensional manifold is low-rank by construction, and our model can actually be used to have predictive models, forecast. So we have enabled forecasting for our models. Finally, we have made our codes available on the GitHub, so I suggest you just use the code in your applications and just keep us posted about the comments.